So it is really so just I can tell that I'm sitting on two chairs or bridging the gap, so just it may be interpreted in different ways. And actually you see that there is expressibility and decidability, and that's math, of course. And still there are applications, and I hope that it's the case when this mesh goes from applications, and that's interesting because so from applications we get some new problems to solve. And of course I do understand that so only some of people listening this talk are involved in this topic, so just I'll try to explain all from the very beginning, and then also just you're welcome to ask questions, to interrupt me, because so just it doesn't make sense to talk to myself, you know.
Yeah, we will interrupt.
So yeah, the outline of my talk, so just it's very straightforward. First, so what is it all about and why? So main questions, why do we do such things? And then I'll speak about formal models, and so just aspects of modeling concern such things as expressibility and the decidability of semantical properties. Here it's behavioral properties, also a synonym. And of course there are also pragmatics. Such aspects are also important for modeling. I will not speak much of that, but still I am to mention it to explain why we consider this or that models. And then actually, of course, so it's a very broad area of modeling concurrency, and I'll speak only about automata-based formal models and more so concrete about patterns and their extensions. And I'll speak about them also. There is a huge topic, but I'll speak so looking from expressibility and decidability issues. So, and then the first question is why, and the answer is, of course, that software reliability is really crucial, and of course, so just there are some horror stories about bugs in computer software with critical consequences, and I will not tell you much about that, so you can find plenty of such things in the internet. And then, so just what to do, how to make our systems reliable. And then, so just also I cite an authority, and Edgar Dijkstra was almost the first who started talking about that. And testing can show the presence of errors, but not their absence. It's already an aphorism everybody should know, of course. And so just, of course, then if not tested, if we would like to prove that our software, our program, our system is correct, then of course we need math. And so we'll speak about verification, but first I'd like this example, and maybe also to entertain you, to tell an example why testing is can't help in some cases. And a very simple example here I can use bit of this blackboard. So just imagine the situation that, so of course we all have bank cards, banking cards, yes, and then so just we use them for receiving our salaries or stipendium or anything, and we have a student who has some sum on his card, and the procedure of sending new sum of money would be like something like so first read what is it, yes, then so increase or decrease, so I will consider increase, and then so just write it, write the new sum. Yeah? So to read.
So you mean it's procedure for what?
For putting, so just for sending your salary to your account.
Oh, so it's a banking system which
yes.
deals with the...
Yes. And then so just there is a student with, say, 0 here. And then so just he is to receive his stipendium, which is, I don't know, 2,000 rubles, if he's lucky. And then also some, so just he had some work and it was very good, and it would be, I don't know, 50,000 rubles. And they come almost simultaneously. So, of course, he expected to receive 52,000 rubles altogether. But what can happen? So we have 2 concurrent processes of this kind. So it could be the first reads 0, the second reads 0, the first computes 2,000, the second computes 50,000, and then what it will be, so just who will be the first? You see, so actually, this very simple procedure of 2 concurrent processes, very simple processes of 2-element actions, can give us 3 different results, either 50, 52, or 2. And if you try to test such system, so you can run it 100 times, and it will not happen, this case. But if you have a real banking system, you'll have troubles of this kind for sure. So it's a very simple example showing that we really do need analysis of such systems. We need verification, and how to do it here, of course, data is irrelevant. So it is about communication, so it is about behavior, and we need models for modeling behavior of such systems and for verification that some concrete properties are valid, and then we can be sure. So for verification, what do we need? We need to construct a model. So I skip all this. I can speak, so just of course, about why not to verify real programs. So different aspects are there. First of all, a program can be very complicated for verification. The second is that it's better first to construct a model to verify it, and after that to develop a system. It's the usual way to do. And then, concerning verification, to construct a model, to formulate a property, and to check the validity. Yes, it's the usual scheme. And then what type of model to consider? Because we have, because it's also not so easy. So just that's a slide showing what shall we understand when we speak about behavior. So it's an example of a RAM, so just very general representation. So we have a state, and an action changes the state, and so on. And we can pay attention either to states. We may be interested in state properties, or we may be interested in sequences of action and possibility of for action to occur. So it depends. Then, if you look at the software programs, then we can easily know that there are 2 very different types of programs. The first type is the so-called input-output programs or state transformers. These are programs which compute something. So we have input data, and we are to make some computations, generally speaking, and to obtain the result. And sometimes they are also called state transformers. And there are approaches for verification of such programs. So actually, such things as Hor's logic and different variants of such things. And there are reactive systems. For first type of systems, non-termination is crucial, so just we should terminate and get a result. But there are another kind of systems called reactive systems, where we wouldn't like it to be terminated. These are such systems as operational systems, computational protocols, workflows, and all kinds of such things. And we have plenty of such systems now with this cloud computing, internet, everything here, and multi-process systems. So for such systems, we often can actually so we just forget about concrete data. We are interested in verification of control aspect of their work. So, and we shall speak about this. That's a picture I like, showing that, of course, so just we do need math, so we can't just believe only that clever programmers will do everything in the right way. Then, of course, we would like to construct a model and to verify it, but there is a right theorem saying that actually, if we have a Turing power computation, then every property is undecidable. Yeah? So, what to do? Then, of course, we can restrict our modeling facilities, and we can consider such modeling language that will be not too expressive to have some properties decidable. And that's actually what I'm going to speak about. So, speaking about modeling behavior, so just we can not so just abstract from data, I would say, and so we consider sequences of events and states, so only are control states. So, of course, sometimes we look at states. And the easiest and well-known modeling facility is finite state machine. So, it can be used for modeling sequences, of course, so just usually finite state machines are used for compiler theory and such things. But actually, we can look at their behavior as runs, yes, so just sequences of actually words, and we can consider finite words, but also we can consider infinite words. So it's just technical detail. Either we can forget about final states and just consider all paths in our finite automata, or we can consider Bücher automata. There are variants, so, but it's also will not speak much about it. So when we have finite state machine, we have a possibility to model the sequential behavior. And what do we have? So of course we have rather limited expressibility, still enough for many applications. What is nice, all properties are decidable. So actually all, yes, so just we have a finite graph and we can make all kinds of analysis. And pragmatically it is also good. Here is an example of finite state machine. So just looking at this, it can be considered sometimes such models are also called transition systems, because no final state, we can consider infinite behavior. This is an automata which can run forever. And then we have labels on arcs, they correspond to actions. But this is for sequential behavior, and we are interested in modeling concurrent behavior, what to do, and so there is an extension, in some sense, actually it is an extension, of finite state machine called Petri-nets. And I'll explain now what is a Petri-net, and it comes from Carl Adam Petri. You see the photo, and I switch to the next photo slide and then return to this definition. We can easily convert finite state machine to a Petri-net. What was done, so just we put a new node for an action. So now we have two types of nodes. Circles are for states, and these blocks are for transitions. And this is exactly a Petri-net, which is a special kind of Petri-net because it's an automata net. returning to, I'll also show the next picture, and then we'll return to. Now, if you would like to model the concurrent behavior, here we also see actually two finite automata. One process, the first process and the second process, and they communicate. So just the individual behavior. So the first one can send message, then he's waiting for acknowledgement, and then he receives the acknowledgement and returns. So just cycling infinite behavior of that kind. And the second agent is a receiver, so similar symmetric cycle. He can receive message, after that he sends an acknowledge and returns to the initial state. Then they communicate, and now having this exact node, so explicit nodes for transitions, we can add communications here, so just we can add buffer, which they use for communication. And now it's a patronage, so we can easily now represent concurrent behavior. So some transitions can fire independently, but some need coordination, and it is done with these additional local places for buffers. And now I'll return to the definition. So what is a patronage? A patronage is a structure which consists of a finite set of places, circles, then a finite set of transitions, and of course they should not intersect. There is a flow relation. It is a bipartite graph, so a flow relation goes from places to transitions and from transition to places. And arcs may be weighted. So default value is 1, so it's just for control, but also they can be used for querying resources. And then we define a state here. So what is a state? For a finite state machine, a state is just one of these nodes. And here, a state is defined by a marking, which maps a set of places to natural numbers, including 0. Now, so one more just illustrating example, because now we can model concurrency in a natural way. So here, transition 1, so we can switch to, so now we have tokens, these black dots, in 2 places, and T2 and T3 can fire concurrency.
So this natural numbers which were in the definition are just the number of tokens in each box.
No. They are ascribed to arcs, and if no numbers are shown, they are ones. Just.
So this is a number of token
consumed and produced.
Produced by.
Yes. And so just I'll also show an example about the firing role. So just how can we define the dynamics? And the rule is as follows. So we have here a transition. We have input places with arcs going from places to transitions, and output places. So here it is H2. And then, so the rule is as follows. Here you see labels, arc labels 2, meaning that so just 2 tokens should be consumed from H2, 1 from O2, and 2 tokens will be produced to H2O. Then, so this is...
It's somehow confusing because this O2 is
no,
one token or 2 tokens.
No. It's two, I mean...
Just each black dot is what? Is token.
So this is a place, a circle. So this one kind of node, another kind of node is transition.
Yeah.
Then we have arcs, as in bipartite graph.
Yeah.
And then these black dots are tokens.
Yeah.
They designate marking. So now we have a patronage with the marking, which maps this plays to 2, this plays to 2, and this plays to 0.
What token will stay there? And the other
Tokens are for state.
Yeah, I understand, but
And these 2 is for...
but the transition takes only one black dot.
Here, yes.
Yeah.
Yes.
Because it's an O2, which creates an
O2,
impression that there are two atoms of O.
Because it's just...
So each O2 is one token.
O2 means that, so interpretation of this formula,
Yeah.
yes. And then, so just a transition is enabled, so it can fire. If it has enough tokens for firing, that means there should be at least 1 here and 2 here. And when it fires, then it consumes these tokens and produces the number of tokens designated with this arc. And of course, it is not just moving tokens, because they can be produced or they can be consumed. So the number of tokens can change. So that's the definition of one-step behavior. And then, so how to define the behavior? We say that the behavior, we can define a run as a sequence of such firings. And then you should immediately ask me questions. Well, so you define the behavior as a sequence of firing, and where is concurrency? And actually, there are some details. First, it could be that so for a given pattern net, several transitions are enabled in a given marking, in a given state. Then we can non-deterministically choose any of them. And then we have non-deterministic behavior with a set of runs possible for this initial state. And then we can actually interpret concurrency with so-called interleaving semantics. That means that we model concurrency with non-determinism. If A and B can fire concurrently, we say that either first A and then B, or first B and then A. That's the case. Why can we do this? We can do this because for most behavioral properties, it is the same, either we consider such semantics, interleaving semantics, or true concurrency semantics. We can define also another kind of concurrency with showing actually concurrent behavior. We can do it in several ways. But for verifying properties, this is enough, and that's very good. So we can just associate a set of runs with each pattern net. Then I skip all formal definitions. I think I'll explain everything, yeah? Then, concerning expressibility of pattern nets. So, of course, we've seen already that pattern nets are strictly more impressive than finite state machines. Actually, so we can just draw transitions on arcs and get a pattern net for each finite state machine. Then, how to compare with other computation models? So, of course, we can define languages for pattern nets. So, just we can either add some final states or anything. It's a technical thing, but we know Chomsky hierarchy. For pattern nets, it is completely incomparable. So, if we look, for instance, for context-free languages, then it turns out that languages of pattern nets are incomparable, meaning they intersect, but we have context-free languages which can't be modeled with pattern net, and we have pattern net languages which are not context-free.
But pattern net language is just a sequence of transitions.
Yeah? Sequence of transitions, yes, exactly.
And maybe you can just give some example of both cases when they are more powerful or less powerful in the context.
Oh.
Is there some, if there exists some simple example just to help us understand the power of this?
So it's...
because pattern nets of course can count. So it's more free, more powerful than finite automata, because you can check with an equal number of this and that. But for
So Petronets actually can't count. So just it's easy to understand that we can't model context-free languages because you see. So just it's not a proof. It's just
some idea.
It's just some idea. For Petronets, so just it is enabled if there are enough resources. But you can't put a condition that a transition fires when some place is empty. Yeah, so it may. So if there are enough resources, it may fire, but it may not fire. Something else may fire and use these resources. So you can't check that there are actually, to say, n tokens in a place.
yeah,
You can check that there are more than n tokens, but you can't check equality. Checking equality is crucial for Petronets. And a bit later, I'll tell you that adding this, you'll get Turing power formalism.
I might be mistaken, but maybe n, so maybe a in power n, b in power n, and then c in power n can be modeled using Petronets, but can't be modeled using context-free grammars.
so
No,
no.
it can't be. Because it can't count. I think something like inequality. Inequality. So I'm so used to this that I wasn't thinking about it for a long time. I forgot
We can find
some
a
good
n
example.
times then b n times, because initially we have n tokens. So we fire a n times, then b n times, and then c n times.
But you say that a n times and b n times without c. Is
we can model
context-free?
with c and without c for Petronets.
So you think we can model A and B N?
Yes.
How do we do this?
If we will specify that we have a final
So
value,
exactly this we can, of
Yes.
course, because then so there will be no possibilities for any other transition. So the rule is as follows.
It can be a useful illustration for us who do not are accustomed to this. So A and B and how do you do this? If you
this is not trivial. I found it on the internet and I don't remember exactly, but I can say that it's not trivial.
It's not trivial actually.
Like this, but
I'm also afraid that
even with two letters is not trivial.
even with two, and with three, it's the same, but a little bit bigger with the same construction. So something like this.
So you're worried that that all the A's finished before the B start? Is that the trouble?
Yes.
So, but you could just intersect it with a regular language, A star, B star, C star, and then that would. So if it were context free, you could then say, if I have the intersection with a regular language, it would still be context free. So it could have been context free.
Yeah, but the question is how do we respect the net?
Well, I think the suggestion is you have three transitions, tokens start, and they move by process A one at a time to the next state, and then you move by process B to the next state, and by process C to the next state.
And how we intersect them.
No, I'm afraid I'm not ready for this question.
Okay.
I'm sorry.
Sorry, yeah.
So just I know that's it, but it's not just to show a very small example.
Okay.
So sorry. Then, what kinds of properties are we interested in? So properties for Petronets could be such like boundedness. First of all, so it is not a finite state machine because I'll show an example. So just the number of reachable states may be infinite. Reachability in the usual case, so given an initial state and the target state where the target state is reachable from the initial one. Coverability, it says that given an initial state and the target state, we would like to know whether we can reach a marking covering it. Covering means that in each place it has at least this number of tokens, or maybe more. And deadlock freeness, so just clear, so it can't come to a state where no transition is enabled. Liveness, so just it's opposite that we can fire transition from any reachable state, so no deadlocks. And there are different kinds of liveness actually. So to analyze battery net, we can construct reachability graph here with an example. For this example, it is a finite structure, so it can be analyzed. And so you see a marking is a vector, so we can fix some order of places. A marking maps each place to a natural number, then we have a vector of natural number. And actually there are such mathematical structures as vector additional systems, and actually they are exactly equivalent to battery nets, just in another form. So then we can construct the reachability graph, and of course we can get some information about it, but that's a very simple example of a battery net which is not bounded. So here we have this producer and consumer and the buffer. Yes. So maybe to explain. So this producer may do his own thing, so produce something, then come to this upper place. Now he is ready to sell an item. So just this transition fires. A producer is ready to produce the next item, and the item is kept here. A consumer may take it from here, but of course it is not bounded, this place. So we can have there as many items. And
maybe it's worth translating the Russian words. It's
oh, no, but
I
I actually told, yes, so it's producer, it's consumer, so just this is producing something and then sending, and here receiving and consuming. So
just to make sure I understand, the producer can only make a new thing after he's sold the first thing, right? And the consumer, when he's bought something.
Yes, so here he can. It could be that he has, for instance, two workers which consume these items, and actually that's also nice for battery nets. So you see,
the buffer can contain several things. Yeah?
several things, yes.
So it's possible that the producer makes a lot of things, and all of them are put in the buffer.
Yes.
Yes, but here you see, so these arcs are labeled with one, so just they can't do it simultaneously. So one by one.
Okay. So that's the only reason it's not bounded is because of the buffer.
Yes, and so that's why we have the reachability set is infinite, and that's why we need some special methods for analysis of behavior. So it's not the case of finite state machines. Yes?
When we define, when we associate a language to a battery net, do we require some special end state of the battery net? Or all the end states are okay?
So it concerns languages of battery nets. Yes, when we define languages of battery nets, and there are several variants of doing this. Yes, of course, we artificially, for modeling behavior, we do not need final states, but for defining languages, to have languages of finite words, of course, we add these final states.
And what means final state?
So we can add a label, as far as I remember, just to label some. I think we can. I remember. For a long time I was not looking at it. It's so.
Also, we need to start to have some tokens somewhere at the beginning.
Yes, so we have it. We have the initial state always.
Initial state.
We have the initial state.
Only the place, but the tokens also.
So we have, yes, initial state, meaning, so tokens residing in places, yes? So we have the initial state, and we have, and to define languages, of course, one thing is to define that when we deadlock, then we, of course, generate a finite word. Deadlock when no transition is enabled. Yes? So there are such possibilities. And then another way is to, I think even they can be converted one to another. Also, I haven't looked for these language aspects actually for a long time. And I do not remember the details, but it can be done technically in several ways. They are more or less equivalent or almost equivalent. And then we can consider languages. But it is clear, so just comparing finite state machines, it is straightforwardly clear. So just we can artificially add some final markings, for instance. Yes, and so here we see that we have also this unboundedness. Yes. Then this is another example. It's a problem of mutex actually needed for solving this problem I mentioned. So just it shouldn't be allowed that so just there are two processes, each going its own cycle, and then so they can visit critical section. Critical sections here means working with some bank account. If one process is working with my bank account, nobody else should be allowed to work with it until the first process completed all it was to do. And this is very simple, of course. It's all these are two examples. So what is done? So if now there is a key, so a general solution, if the first process would like to enter critical section, it should check that key is available, then it takes a key and returns it only when he leaves it. And then so just when the key is used, then the second can't enter critical section. So that's also, and then the safety property here would be that two processes can't be simultaneously in the critical section. Of course, it's not something, there are interesting protocols for solving this problem. Of course, this is just a very general scheme. So here is another Petri-net for well-known problem of dining philosophers. I will not talk much about it, or I am afraid I have no time for main things at all. And so just and here, so liveness and fairness is important here. So we have processes which use common resource, and so just there are some limitations, and so there is a problem of liveness, meaning that each process sooner or later will get access to this resource. You can imagine a common printer for several rooms. And so it's called the problem of starvation, when so a process can't get access to the resource, and so just dies from hunger. And so just one slide about a kind of pragmatics showing that Petri-nets actually allow to model in a very clear way main patterns of control, sequencing, choice, concurrency, cycling, and so we can define different kind of behavior interactions. Then, so just to remind, we are speaking about expressibility and how Petri-nets can be extended. One strong extension is to add special kinds of arcs. So with usual Petri-net notation, so this transition can fire if there are enough resources, yes? But we can't express that it can fire only when there is no resources in some places. Actually, this is equivalent to modeling if. You see, so just what do I speak about? In other words, so we can model choice in two ways. So in finite automata, we have just non-determinism, yes? So there is a non-deterministic choice, and we can't put condition here, yes? So we just know it can go this way and this way. To have Turing power, we need if. We would like to check some condition. In pattern nets, it would be to check whether a place is empty or not. But for classical pattern nets, there is no such possibility. And if we add this possibility, if we add a special arc called inhibitor arc, so the rule is as follows. This transition can fire if there are enough resources in this place and this place is empty. With such extension, we can model Turing machine with pattern nets. So we can model any computing on natural numbers. Because we have cycle, we have if now, and sequencing, so we have everything. So that's actually the crucial point.
And without that, it was back-to addition system.
Yes.
And it's a difficult result, but they are decidable.
Yes,
Yeah,
exactly.
yeah.
Exactly. Exactly. Reachability is decided.
Reachability is decided.
So that's a crucial point. And there is a big gap actually, because Turing machines and pattern nets for which actually all properties are listed are decidable. Another variant I have no picture here is a reset arc. It's something in between. So a reset arc, it works like follows. It's sometimes shown this way. So it means that it doesn't matter whether there are any resource, so it may be empty, and after firing, this place will be empty. So it's just to empty this place. So it is enabled when we look whether it can fire, we do not pay attention at it, but after firing, it will be empty. And then we get a quite intermediate case, because for such variant of pattern nets, reachability and boundedness is undecidable. But there are still decidable properties. And what is decidable? Termination is decidable, and coverability is decidable. So the difference between reachability and coverability. Reachability, we have the initial state and the target state, and we ask whether it is reachable. And here we ask whether we can reach a state which covers the target states. And covers means that in each place we have equal or greater tokens. Yeah? So point-wise inclusion. Coverability is very important for pattern net because so just when a marking is greater than, so if a transition can find some marking, it can find in any marking covering the given marking. That's a very important property for pattern nets. So we have this kind of extensions. But for practical applications, we are interested in so a bit another perspective to say for extensions. So if we look at classical pattern nets, then we have I would say a propositional case. So we have just black dots, and if we model a system, that we model it in an atomic way. So there are extensions, so we can switch from usual, classical, sometimes they are called place transition nets. This kind of patterns, to so-called high-level pattern nets. What are high-level pattern nets? In high-level pattern nets, tokens are not just indivisible black dots, they are individual objects. So we can distinguish different tokens, and then transitions can find different modes. Then this gives us a possibility to make a more compact models. So here is a small toy example also I'll use for illustrating this, and this is a usual place transition net. So what does it represent? So it's a laboratory. So here are 3 people working at this laboratory. They can be either at home or at work. They can switch. So they can go home and return to work. And being at work, if there are 2 people, they can generate a project. For that, they need discussion. So you see these arrows goes to and from. That means that, so just for this transition to file, we need 2 tokens here. Then it files and tokens return here. They are still at work. And here we generate a project.
So each place is a multiset. It's not a queue or not. So there is no order. They're all available at the same time. So if they are the same, just dots, then there is no difference between them.
Yes. So
if they are now people or objects.
No.
So
here we just see that. What do we know here? That there are 3 individual people. So indivisible. So how similar people. So we do not distinguish them. And 2 are at home and 1 is at work.
Yeah.
How they get home after making a project?
So they can go home at any moment, even without making a project. So if a token is here at work, then this transition can fire, and then a token comes
so
here.
the token cannot go to discussion.
Yes, it can. So just it's non-deterministically. So if there are even all 3 are at work, they may not generate a project. They do not do projects. They just stay here and then go at home.
Yes, so this token doesn't go there. Just a new token appears in the right one when the discussion happens. Yeah.
Yes. So just for this transition. So now you see here.
This
transition is enabled. It may fire, then these tokens go home. This transition is enabled. So it may fire and 1 token goes to work. Now this transition is not enabled. If there were 2 tokens here, then it is enabled. After firing, there will be a new token here, a new project, and still 2 tokens here. So, and I use it just to illustrate high-level patternnet, because now we have individual laboratory staff, and we have 3 here, A, B, and C. They have their names. And then now you see it is high level, we have variables here. What for? Because now this transition T2. So just, of course, we can model it with classical patternnet. For that, what do we need? We need a separate cycle of going home and at work for each member of the laboratory to distinguish them. But now we use as a common place at home, and we see that A, B are at home and C is at work. Now, about firing this transition. We have this variable, and it's better to look at P1. So it is enabled, but it can fire in 2 modes. Either X is equal to A, or X is equal to B. X is variable. So just to define a firing, we consider binding variable, so assigning it a value. And with such an assignment, if it is enabled, then it fires with this assignment. So this X is bounded with this one. So of course I would write Y so at the upper line, you see. So this, if I define binding for this transition, then it should be I assign X a value, and then this x should be of the same value. So, what do we have? Here, of course, we have a more compact way of modeling concerning expressibility. If we have finite number of types, then we can translate it to classical pattern net. And if we allow infinite types, for instance, integers, then it will be Turing power. There are several kinds of such concrete extensions. The most popular are so-called colored pattern nets, and they allow integers, natural numbers, but then they become Turing power. And then what is good and what is not good with these high-level pattern nets? What is nice? Of course, it is much more compact, nice to understand, and all that, so just good for modeling. Another thing is that some methods of analysis can be done without translating to the classical pattern net. And when we translate it with finite number of time, so it grows exponentially. So it's a real, so it matters. And then, so concerning expressibility, we have still the same thing, or Turing power. And then one more variant, another kind of extending this example. And now we have here dynamic tokens. Now tokens are pattern net themselves. And this is a very simple case when our people, our staff, can, so is a pattern net which can be in two states. It can be either active or passive. And there is a cycle, so it can switch from one to another. Then how to define behavior? It looks like high-level pattern net, and this transition fires as for high-level pattern net, so it's an autonomous transition. It may move a token, net token, from this place to this place. That's, it calls system autonomous firing. Another kind of firing is, of course, also a transition may fire inside the token. But it wouldn't be interesting if they can't synchronize. Here, what do we see? We see that this transition is labeled, especially synchronization label, and this one. It means that they should fire simultaneously. Now we have such a situation. So when a net token, so this submember is passive, it can turn to an active model independently, being either at home or at work, anywhere. It can become tired only after generating a project. So here it is synchronized with this. So step by step. So it can go home, it can return, it doesn't depend on the state. If you have two net tokens here, so this transition can fire only when this transition is enabled in both net tokens. We say these net tokens are involved in this transition. So, for this example, it can fire only if they are both active. So if we have two active net tokens here, then it can fire. What is the result? Here we have a black dot, and here we have two tired staff members. So that's a vertical synchronization of this system. So what do we have? We have a more compact way to describe complex behavior. We have dynamic objects. They can move in a system net. They can do their autonomous actions, and they can synchronize. So it can be helpful from pragmatic point of view. But we are interested in that thing. So that's another picture, sorry, with Russian subscription, showing a possible marking of such a net. So we have net tokens, each net token has its own marking. So, concerning formal definitions, so there are actually some restrictions. And I still tell that the aim is to obtain a system which is still not Turing powerful, actually. And for that, we need some restrictions. So, what are arc inscriptions here? It could be variables, sums of variables, if he moves several tokens. And there could be constants. Constants here mean concrete net tokens with some initial markings. What is not allowed? It is not allowed that we have an outgoing arc marked by constant. What does it mean? It means that to fire this, we should check the inner marking of our net token. And checking inner marking is actually equivalent to checking that some place is equivalent to 0 in classical pattern net. So it's just intuition, but it can be proved, you see? So it is not allowed. Also, we do not allow comparing inner markings. So it's like in a pattern net style, so we can't see the exact marking, but we can check whether there are enough resources to do some transition. And the same for these net tokens. So we can't check whether they have, so this would mean that they are similar, so they have the same marking, that's the same. We do not allow it just syntactically, it's easy to do. And then, so I'll skip all these definitions, I'll explain you the behavior with these pictures. So that's the marking. And we have several kinds of steps. So autonomous steps in a net token and in a system net, when we do not look at inner markings at all, just move or consume or produce objects. This is autonomous step. And we have two kinds of synchronization steps. Also, I could add horizontal synchronization, so net tokens which are in the same location can synchronize, just doing some, we can add labels, doing some transitions only simultaneously. So we have two tokens in the same place, and they are labeled for horizontal synchronization. That means that this transition may fire only when there is another net token with the enabled transition with the adjacent label. So a bit. And vertical synchronization was explained. Then you'll tell me about the time, yes, if needed.
Yeah, but still you have 18 minutes.
Fine. So now the main thing actually, so just about the expressibility and decidability for such kind of pattern net extension. So, first of all, it can be shown that with such nested pattern nets, we can simulate reset arcs. And it is clear, how it can be done. Actually, how to empty a place. We add a net token with this place, and we remove this net token, and that is, we remove the entire inner marking, yeah? Any number of inner net tokens. So this picture shows So you tell me if you are interested in details, but I'm afraid you are tired already with all that stuff. So what follows? Then we get that nested Petri nets with these restrictions, as it was defined, are strictly more expressive than classical Petri nets, because they can simulate reset arcs. So we have that reachability and boundedness are undecidable for this model. Then what is decidable? Still, we can prove some decidability. First of all, we consider so-called multi-level nested Petri nets. What is multi-level? I showed you a system of 2 levels, but it could be several levels. So just net tokens, maybe also nested Petri nets, and so on. And then a system is called multi-level, is the number of levels is limited. It can be easily checked syntactically on syntactical level, because so the unbounded number of levels can be generated only via recursion. I'll show you an example how it can be done. But if it is not the case, it can be checked syntactically. Then we prove that for such systems, I skip technical details, that termination problem is decidable for such systems. Then control state maintainability problem, which means that so just we can always fire one of some set of transitions, and this is a dual property, inevitability property. They are decidable.
Can you say about complexity? How really?
Yes, so it's not, I was going to tell at the very end, so just I didn't analyze the complexity, but it is well known for classical Petri nets, the complexity is extremely high. So it doesn't even make sense to look at complexity here, you see? Because, so just classical Petri nets is a special case for
still probably we hope somehow that at least in some practical situation it can I'll tell
of hope. Yes, I'll tell. So just at the end, first I'm going to give a very general picture, which is not, of course, so still it is nice, it is decidable, so just which is not obvious at all. And what is nice also that we have, so not with these reset arcs, but with this formalism, which so just follows some intuition about individual agent behavior. So it is strictly between Turing machines and Petri nets. And how decidability can be proved, so just I'm going actually to skip it to tell something else, but it's the theory of so-called well-structured transition system is used, and the idea is very nice and very easy, and I'll draw a bit. Yes. What is a well-structured transition system? First of all, Petri nets have such a nice property that, so I've told, if we have a marking, and this marking M prime is greater than a marking M, and in a marking M we can fire a transition or a sequence of transition T and get some M1. Then here we also can fire T and we get M prime 1, which is also greater. Yes, and that's one property which is needed, and we also are to define such ordering for these nested Petri nets. And here as a marking we have a special kind of tree, so we are to define such ordering for the marking. But another property which is needed, this ordering should be well quasi-ordering. And well quasi-ordering means that for any infinite sequence we have at, should I write or I can skip?
No, just every infinite chain stabilizes, yeah?
Not exactly. So in any infinite chain, we have a pair where one is greater than another.
Oh, sorry.
Yeah, that is quasi-ordering. And so we are to define this quasi-ordering for markings of nested Petri nets, so that this diagram also is valid, and that makes them well-structured transition systems. And then there are some results of general theory of well-structured transition system, which helps us to check this property. And then a bit further, so that's about well-structured transition systems. So it was done by Finkel and Schnobel in this theory. And then that's about quasi-ordering. I'll skip it. So these are the decidability results, because I would like to show you also the recursive case, which I consider very interesting. So here you see an example of a nested net, and here we have two nets. So this is a system net, it's a net token, and here we have a constant, which is this net token. So that means that firing this transition generates here this net token. And what is important, here we have also the same f. So it is recursive. That means that it can recursively, so it generates this net token. This net token fires and generates its copy inside, and its copy inside, and its copy inside. And then this vertical synchronization allows us to fold it back, like as in a recursive unfolding and folding, yes? And then we can use, so just define such things in nested Petri nets as well, when we so allow recursion. And then what about decidability? And then for this special case, what is important? So just generating this new level doesn't depend on the environment of this net token. So just its inner state generates a new level. And that is a kind of, so just it is a kind of locality. You see? So just a possibility for transition to phi depends only on its local surrounding, and this local surrounding, looking at vertical levels, is so minimal. So it doesn't depend on the upper level at all. And for such case, so you see it can be done. For such case, we can show decidability results. Even for a bit, that's an example how it can be unfolded, a reachable marking. And then it can be also folded, here I told it. And these are, I call them nested Petri nets with autonomous elements. And another, I can generalize it to some such thing. So I say that the behavior, so I have, this is a marking, which is a true. I have a net token at some level. And the behavior of this net token may not depend on the upper levels, but may depend on some levels. If so the influence, so the number of levels on which it depends is limited, then I have a kind of locality. So for classical Petri nets, we have this locality property. So just firing off transition depends only on its local surrounding, and it corresponds to the idea of distributed systems. So distributed systems do not have global view, they know their neighbors. So if my behavior depends on somebody who is 1,000 miles far, so it's not good. It's not a good system, it's not real. So I have my own limits, so of dependability, and if, of course, it is not true that, so just I can construct a nested Petri net for which it is not true. But for such nested Petri nets, I can obtain decidability results. And these Petri nets are called nested Petri nets with localized elements. And for them, we have here, we can't apply theory of well-structured transition system. It doesn't go. But, so some special tricks and special constructions allow to show that termination problem is decidable for such a construction. So it is still not Turing power. So I think it's, for me it's interesting. I do not think it's a practical question. I think it's interesting from the point of view of computability hierarchy, and some more hierarchy. And so just if we consider general case, it will be Turing power. And here is this hierarchy. Yeah.
This theorem, what's the complexity of the algorithm?
So just I didn't do any estimation, but actually the algorithm considered, so just to prove decidability, actually I construct some algorithm. So just of course it can be, just you can compute this, but it is, so it's for sure it is a high exponent, so just it is even not interesting to look at. I didn't look at it.
And for classical Petri nets, the reachability, are there some lower bounds for complexity?
Yes, I'll tell it here. So I have it. It's
with respect to some.
here.
X space.
X space had so reachability problem for classical Petri nets. So doesn't make sense to measure complexity here. So that was for conclusion, just answering your question. So of course we have very bad complexity, extremely bad complexity in all these cases, but it happens that still, and when we have models with some decidable properties, they are somehow nicer. And then we can analyze special cases, and we do such things. So these are two recent works with Leonid Dvorzhansky. So just these are structural methods, so they are also known and applied for classical Petri nets. And these are just considering components, net tokens, and system nets separately for some analysis, some compositionality. And if I have some minutes?
5 minutes.
Yes, then I'll return to slides I skipped because I consider it's very interesting. So that's hierarchy. We have ordinary Petri nets. There are Petri nets with reset arcs. There are also recursive Petri nets of harder than Fatranor I didn't define. But for them, reachability is decidable. For this class. For this not. Then we have multi-level Petri nets which come here, and recursive nested Petri nets with autonomous elements, so they include, so we can model these recursive Petri nets. And then we have Petri nets with localized elements, and then we have general case. So.
And in some cases you have inequalities. And in other cases?
In other cases, there are some open questions. Yes. So actually, there are some open questions. Yes, but I was not looking at this for a long time already. And another comparison. So I think that's interesting because it is always interesting to look at intermediate cases, just to have some natural way to define them.
Sorry, where's the decidability boundary here?
Some properties. So reachability is decidable here and here only. And here I don't know actually. I didn't check. And for role classes except Turing, something is decidable. Termination is decidable, for instance. And then one more picture. So that's comparing with process algebra. So I didn't speak anything about, didn't tell anything about that. But actually, these are all actually equivalent to finite state machines. So this is to context-free language, which is analog with process algebra with infinite sequences. And then we have this is patterns, and this is nested patterns.
We can only guess what all this is, but
yes, but it's clear. So the very general idea. This is patterns which are incomparable with context-free with recursion. Actually, for process algebra, you have recursive definitions, and you have context-free languages for nothing, of course. And then but they are incomparable. But nested patterns include, both types. And there is another formalism also which includes this, and but for which, so not everything, but this BPA, for which reachability is decidable, that is process and writing systems. So, and that was my conclusion.
Okay. Any questions? I have a kind of general question.
Yep.
So I'm completely outside this field, but I remember quite well that 30 years ago I read very exciting, nice papers about different primitives for concurrent programming, for semaphores, monitors, this and that. And there were languages like concurrent Pascal and Occam later, and communicating sequential processes. And and people say that, look, we are now preparing for the future when there will be thousands of processors, and we develop the languages, and it will be very important, and so on. And now we see that really there are thousands of processors and millions of processors, and still, for example, popular operating systems like Linux are written with some very special threads in the kernel, which are not using any advanced things, which are very a lot of errors.
Yep.
So somehow it seems that there was some theory, and actually when the practical need comes, the theory is forgotten.
No.
And it looks strange. Why?
No, it is not the case, actually, because now there are actually tools for verification. Of course, so just you are a mathematician, you believe, understand better than anybody else that there can't be miracles, so we can't verify everything, that's all. But for many cases, they do have successive stories. And for instance, in program systems, Institute for System Programming, Ivannikov, yes, they do verification of Linux drivers quite successfully. And so there were examples of finding bugs with patterned verifications, and of course now there is model checking technology which becomes actually practical.
Yeah, but it's not I don't want to say that there is no theory. I just want to say that there was some kind of field, like developed safe and efficient languages for parallel programming. And strangely, instead of developing this stream, they started to apply very delicate analysis to
programs which are already written using in Linux, using unsafe C, unsafe threads library, and for outsiders it looks very strange. It should be something which prevents people to develop this.
It actually have a prehistory in Pascal. So maybe you also remember that Pascal was developed so just having Horace logic rules in mind, and it was so declared that programming in Pascal in structured manner will so just help us to not to make bugs and all that. But of course it's true and lie at the same moment, because of course so we can't do formal verification automatically, but we can do many things, and we can't develop a language with the error so without errors, I don't know, but we can use patterns or some technologies for verification, and now many things when they are developed, they are so just first modeled and verified and then developed. That's it.
But I would say, for example, for Pascal and in loop invariants, actually, really every winner of international ACM competitions knows quite well what is loop invariant and doesn't use Go-to in his program.
Yes.
But still, I would expect that at least some of these tools developed for specific concurrent languages should have some practical importance, but it seems that these languages who now use OCaml for drivers or something's happened, but it's not clear what.
So actually I'm not a specialist in programming languages, that's it, but because I am speaking about model verification, yes, and about modeling, and then there could be some methods of analysis. It is more analysis than verification. And then of course these methods can be used for some, yes, and then of course so just my belief is that there can't exist such a language, of course, but when we do these studies, theory studies, we understand things better, and then we develop better languages. And that's the only thing. I think it influences this way.
Okay, so any other questions or comments?